Hey Pre-Calc, this is part 3 of the 5.2 note section. So this one's probably the most sophisticated type of them, but hopefully you'll find it's not too terribly difficult. So what happens if you have a right triangle, but you are sorely missing a lot of pieces of information? Like we have one side of the right triangle, we've got the fact that it's a 90 degree and a 39 degree angle here, but we don't have a side. We don't have a side. We can't use the Pythagorean theorem to find the other sides. What do we do? Well, here's what we can do. What we can do is first, if it says solve the right triangle for all unknown angles and sides, well, we can certainly find this unknown angle here. 90 plus 39 plus our unknown angle have to add up to 180 degrees. So a quick shortcut is to say that 90 taken away from 180 is 90. So you're just taking 90 minus 39. So 90 minus 39 gives us 51 degrees for our unknown angle. So we know this in the corner here is 51 degrees. So the unknown angle, that was simple enough, is 51 degrees. And you can even like label it as theta to just say like, hey, theta equals 51, that's my unknown. Now, what are we supposed to do to try to figure out what these unknown sides are? I'm going to name them. I'm just going to call them A and B because that's what they look like for the Pythagorean theorem. Why not? So just pause the video for a second and see if you can think about any strategies where it's like, hey, we're dealing with trigonometry. We've got a task here that can't be done with the Pythagorean theorem. What could we maybe do using trig? Pause the video, think about it. Okay. So no, really, pause the video, think about it. Okay, you've thought about it. Think about the information we're given here. We have the hypotenuse's measure. Sine of theta equals opposite over hypotenuse. Ooh. Additionally, cosine is adjacent over hypotenuse. Awesome. Okay, here's what I'm getting at. I've got an equation. I got two equations in which if I took the sine of the angle given, that's actually going to be a real measurement. Like I can punch in sine of 39 degrees on my calculator, and that's a constant number. The hypotenuse is a constant number as well, 17. So it's sort of like I got an equation with 1, 2, 3 unknowns. Now we've got one of the knowns and the second unknown. I'm down to one unknown with one equation, and we can work with that. So we're in luck because you can pick either one of these angles. Let's just pick 39 degrees. And say we're trying to solve for the opposite side. So I can say that the sine of 39 degrees equals opposite, which is A, divided by the hypotenuse, which is 17. Now think about this. If I put my calculator into degree mode, because we're talking about degrees here, 39 degrees. Oh, we haven't even talked about radians yet. That's equal to this decimal. We can round it to 0.629. You know what? Or we could just leave it as it is here and then do the final calculation of sine of 39 degrees as it relates to the other numbers. Because look, A divided by 17, you can get rid of division by multiplying. So if I multiply by 17, it cancels the 17 out here. Multiply by 17. I just take that decimal right there, multiplied by 17, and I found A. A is approximately 10.698 whatever units this is. Got it. Similarly, if I'm working from 39 degrees, I could use cosine. What's the cosine of 30 degrees ratio going to equal? Well, it equals the adjacent side to 39, my other unknown b, divided by the hypotenuse 17. Okay. Get b by itself. You're dividing by 17, so multiply by 17. That cross cancels, multiply the other side times 17, and let your calculator do the rest. B is approximately 13.211. And we just solved for all the missing parts. I solved for A, I solved for B, I solved for that unknown angle. I don't know, do I need to say that that's 90 degrees? Couldn't hurt. All the parts have been made known now. So, you see now how trigonometry is pretty helpful, because there are so many places in real world like mathematics situations where I've created a right triangle specifically with like constructing things and just structural application where, hey, it'd be really nice to know how I can find an unknown side here if I know like one of the angles and one of the constants. So let's check out a different one here. Example 5 gives us some alternate information here. What happens if you don't get any angles at all? So we know that's a 90-degree angle, but let's say this is theta, we'll call it theta sub 1, and this is theta sub 2. They're just two unknown thetas that I could use alpha and beta if I wanted to. They use Greek letters for angles a lot of times. Future reference for bigger math. Now, the unknown side here is going to be pretty simple because we've got two of the three. We can just straight up do Pythagorean theorem. A squared plus 5 squared is equal to 13 squared. And I believe this is a Pythagorean triple where 12, it goes 5, 12, 13. Let's double check. 169. So we know that unknown side's 12. So whenever you're given two sides and none of the angles, the side will always be best solved by just doing the Pythagorean theorem. What are we supposed to do with the thetas, right? Well, this is where we have to rely heavily on this calculator, okay? Here's what I mean by that. We're given, with respect to theta 1 and theta 2, all the trig functions. We got hypotenuses, we've got adjacent sides, and we've got opposite sides. So it doesn't really matter which trig function you use, you just got to make a choice, pick one. So let's just pick theta sub 1. Pick sine, cosine, or tangent. Tangent, okay? What does the tangent of theta sub 1 equal as a ratio? Well, opposite is 12 divided by adjacent leg, which is 5. So we could do a guessing game where you could say, what degree measure creates this opposite over adjacent side? But I don't think we're really equipped with that just yet. So what I'm introducing here is this idea of there is an operation that can undo tangent. Think about it like to undo division, you multiply, right? To undo subtraction, you add to both sides. To undo a log, you exponentiate both sides. To undo an exponential, you log both sides. To undo a square root, you square both sides. Right? So when you apply trig to both sides, there's an inverse operation you can do in which has been programmed to this calculator. And that inverse operation is really easy to remember because it's the tangent inverse operation for this particular thing. So here's what I mean. if I apply tan inverse to the left-hand side, because if you'll notice, on your calculator, there's the tan button. See that little tan inverse right above it? Here, I'll get real close for you. Woo. Okay. That gets rid of the tans, and you're left with theta sub 1. But on the opposite side, you're left with the inverse tangent value of 12 over 5. So what you got to do is, you got to hit second tan. That's how I access the tan inverse function here. And then I put 12 divided by 5 in there. Since I'm in degree mode, it's going to turn it into degrees for me, and I get 67.380 degrees. Now, think about this. Over here I did 2 trig functions to find 2 different side lengths. Over here, once I find one of the unknown angles, now I've got 2 out of the 3 angles of a triangle. So all I got to do is say, these 2 have to add up to 90, because this one's 90 as well. So take 90 minus that. I've got theta 2. It's 22.620 degrees. And you're done. I've got the 2 unknown angles and I got the 1 unknown side. All right, guys, hopefully this was helpful. Kind of fragmented into the 3 parts. It's kind of weird because I have Zoom meetings all day long today, so that's kind of why I had to do this anyway. But yeah, this is a 2-day assignment, and once you finish that and complete it, your semester for pre-calculus, fall 2020, is complete. Congratulations. I'll see you guys. I'll see you when I see you.